Welcome to the Heat Exchange. Every industry has its conversations. This is one about heat. Every week, we sit down with engineers, industry experts, innovators, and the business leaders to explore the technologies, ideas, and trends shaping the future of thermal management. I'm your host, Cora.
Hi everyone, I'm Mona from the marketing team.
And I'm Carlo from engineering. Great to be here.
Today, we're tackling a topic that's top of mind for every hyperscaler, data center operator, and hardware engineer right now: AI compute power. Every time someone prompts a large language model to generate code or process videos, we see the intelligence on screen. But behind these things, silicon dies are generating unprecedented levels of heat.
Exactly, from a market standpoint, the conversation has completely shifted. AI isn't just a software story anymore, it's an infrastructure and thermal bottleneck story.
Which leads us to our core question today. As computing power explodes, how do we keep data centers cool, efficient, and reliable? Today we're breaking down why AI servers burn so hot, how the industry is migrating from air to liquid cooling, and why the heat exchanger sits at the very heart of modern data center architecture. Let's jump into part 1. Carlo, help us set the baseline here. Data centers have been cooling servers for decades. Why is AI causing such a dramatic thermal surge compared to traditional servers?
Great question. Well, it comes down to chip architecture and workload dynamics. Traditional enterprise servers rely primarily on CPUs. They handle tasks sequentially. This means so their power demand spikes and drops in bursts. A traditional CPU server rack historically drew anywhere between 5 to 15 kilowatts.
Right, and to put that in the market term, 10 to 15 kilowatt per rack was the standard benchmark for years. Data center manager built their entire HVAC and air handling strategy around that number.
Right, but AI accelerators like GPUs and NPUs operate on massive parallel processing. When you train a large language model, those GPUs run matrix multiplications at near 100% utilizations for weeks or months straight without stopping. Zero breathing room.
And the individual power drop per chip has soared, hasn't it?
Yes, dramatically. A few years ago, a high-end CPU had a thermal design power TDP of around 200 to 300 watts. Today's top-tier AI chips start at 700 watts and are pushing past 1 kilowatt per chip.
That means a single rack loaded with some modern GPU nodes can easily exceed 40 kilowatts, 80 kilowatts, or even 120 kilowatts per rack.
That's nearly 10 times the power density crammed into the exact same physical footprint. It's no wonder operators are running straight into a thermal wall. That brings us to part 2. How we actually tackle this heat. Mona, from what you are hearing in client discussions, can't operators just turn up the chillers and blow air faster across these racks?
That's the first thing everyone asks. But the market is hitting a physical limit with air. Pushing air faster requires massive fine areas, which consume huge amount of power, takes up valuable floor space, and create noise level that can literally damage hardware through acoustic vibration.
To elaborate, physics simply prefer liquid here. Water has a volumetric heat capacity of almost 3,500 times greater than air. Once the rack passes 30 to 40 kilowatts, air cooling can no longer remove heat fast enough off the silicon die.
So liquid cooling becomes non-negotiable. Carlo, walk us through how direct-to-chip cooling is leading the architecture today.
Absolutely. Direct-to-chip is the undisputed workhorse of modern server design. We attach a sealed metal cold plate engineered with intricate internal microchannel passages directly onto the GPU heat spreader. Coolant absorbs the thermal load straight off the silicon surface, capturing up to 80% of the rack's total heat load right at the source, while managing the remainder via secondary loops. While niche specialized facilities occasionally look at total immersion tanks, direct-to-chip is where most all mainstream enterprise engineering and manufacturing lines are focused.
So from a deployment perspective, direct-to-chip is dominating because operator can integrate cold plate loops and coolant distribution units, aka CDU, into existing air-cooled rack footprint with minimal structure disruption, making it the practical choice for the rapid data center retrofits.
Now, let's get into part 3, which is the heat exchange really comes into focus. The liquid absorbs heat from the GPU inside the rack. But where does that heat go next? You can't just pump raw cooling tower water directly through a multi-million-dollar AI server cluster.
Absolutely not. That's why we divide the facility architecture into 2 completely separate hydraulic loops. The first one is known as the IT cooling loop, and we call it the secondary loop. This is a closed, highly controlled loop using treated deionized water or coolant flowing through the servers and the CDU, which is the cooling distribution unit. And the second loop is the facility cooling loop, which is known as the primary loop. This is the building site's water loop connected to external chillers, dry coolers, or evaporative towers.
And right in the middle, connecting these 2 loops without mixing them, is the heat exchanger.
Exactly. The plate heat exchanger inside the CDU performs 3 vital duties. The first one is efficient heat transfer. It transfers thermal energy from the hot IT loop to the facility loop across thin corrugated plates with minimal temperature loss, sometimes achieving approach temperatures down to 5 or 6 degrees Celsius. And the second would be the fluid separation. It provides a strict physical firewall. Contaminants, scaling, or minerals from the facility water can never reach the macrochannel cold plates inside the servers. And the third would be the pressure and flow isolation. It decouples high building water pressure from delicate in-rack manifolds.
Right, and Carlo, from a commercial perspective, this is where reliability is everything. If a heat exchanger underperform or scale up, the CDU can't transfer heat fast enough. That forces the GPU to thermal throttle, which can cost operator tens of thousands of dollars per hour in wasted compute capacity.
Right, so the heat exchanger isn't just a passive component. It's the critical bridge maintaining balance, safety, and performance across the whole data center. Let's look ahead to part 4, the future of data center thermal design. Mona, as sustainability mandates and energy regulations tighten globally, how is the industry rethinking waste heat?
This is one of the most exciting trends we're seeing. Historically, data centers spend energy just to dump heat into atmosphere, but with liquid cooling, the exhaust water temperature coming off a GPU cluster can easily reach 50 degrees Celsius to 65 degrees Celsius.
And that is high-grade thermal energy.
It really is. Rather than throwing that energy away, operators are using high-efficiency heat exchanger to harvest the thermal output for WHR, which is the waste heat recovery.
Where is that recovered heat being put to work?
Well, the fact is we are seeing facilities connect their heat exchangers directly into municipal district heating networks to warm nearby residential housing, heat industrial greenhouses, or preheat water from commercial facilities.
It turns thermal management on its head. Cooling is no longer just an operational expense. It becomes a circular energy asset.
That is a game changer for ESG goals and a great integration. We started with silicon chips running hot, and we ended up with data centers serving as energy providers for local communities.
And the thermodynamics always points the way forward. As rack densities grow, mastering fluid dynamics and heat transfer is the key to unlocking the next generation of AI.
And at the heat exchange, that's exactly what we help our partner engineer every day.
That wraps up our today's episode of The Heat Exchange. If you enjoyed this conversation, subscribe to our channel, share the episode with your engineer team, and reach out to us if you want to optimize your next thermal project.
Thanks
for listening.
Until next time, stay cool.